Good evening, everyone. My name is Thomas Macri, and I'm happy to start this webinar on called Quantum with Friends, sponsored by QuEra, and today dedicated to our to the quantum ecosystem in Taiwan. I'm happy to introduce my esteemed colleagues from QuEra, as well as from the National Taiwan University, Professor Ying-Jer Kao, as well as Min-Hsiu Hsieh from Foxconn. The agenda will be as follows. I will start with some introduction about QuEra computing that will be complemented by my colleague Ayumu, who is the country manager of QuEra Japan, who will tell us a little bit about the experience of QuEra in the country. Then we will hear about the Taiwan Quantum National Program from Professor Kao, followed by a discussion of QuEra capabilities, as well as the specific software stack that we've been developing at QuEra by my colleague Kai-Hsin. Then Chen will be discussing the recent developments of quantum error correction at QuEra. And as follow-up, we will hear more broadly the quantum strategy, and more specifically the amazing development that Min and his team have done at Foxconn. So with this in mind, I would like to quickly start by briefly telling you about QuEra. QuEra is a quantum computing company headquartered in Boston, Massachusetts. We work very closely with Harvard and MIT. Our goal is to build quantum computers with neutral atoms that are considered by many to be the most promising approach. Our technology is not yet confined to the labs. We have machines that are available on a major public cloud since November 2022. And currently, as we will hear also from my colleague Ayumu, we have a system that has been installed at AIST, the Japanese Center for Standard and Technology. Recently, we closed a major investment, our Series B, at $230 million, which was led by Google, SoftBank, Valor, and yesterday we also announced an investment by one of the major GPU, definitely the major GPU provider, NVIDIA. We, as we will hear a little bit in the next few minutes, one of our goals is to collaborate with governments, companies, HPC centers in their quantum journey. And we definitely believe that these are the major, if not among the majors, if not the major quantum stakeholders available right now on the market. So let me perhaps take a small step back and tell you where are we in the quantum journey. So as you might know, there are many different modalities to perform quantum computing. Superconductors, trapped ions, photons, silicon, as well as neutral atoms. And each one of these platforms has some specific capabilities and can be differentiated based on a number of different items. For example, the number of qubits, their possibility of scaling these qubits or scaling the size of this platform to a defined number of physical elements, whether they are natural, like in the case of neutral atoms, or artificial in the case of superconducting qubits. Some systems may require cryogenic coolings. This is not the case in the specific case of neutral atoms, but many others require to put down or to cool down to very, very low temperature, not only the qubits, but also all the electronics that is needed to control classically those qubits. And this is the case, for example, of superconducting systems. Connectivity is another important feature that matters not only at the level of controlling classically the topology of the system, but also in terms of executing specific algorithms, both at the physical level as well as at the logical level, as we will hear more from Chen in a minute. The other important element is now the availability at the commercial level. We heard that in the first slide that we collaborate with the AWS to provide a cloud service, but we also operate the systems on-prem, not only in Boston, but also in Japan right now. And finally, I don't want to digress too much in terms of capabilities related to error correction or the possibility of running in general complex algorithms, because we will hear more from Min as well as Ed. There are a number of advantages using neutral atoms, and that's why it is considered by many as one of the most promising quantum platforms in terms of scalability, the possibility of operating the systems at room temperature, this all-to-all or long-range connectivity that is enabled by a specific capability called qubit shuttling. Systems have in general high fidelity and relatively long lifetimes compared to other systems. And last but not least, we operate natural qubits, meaning that all the qubits that are our neutral atoms, our rubidium atoms for the systems that we are building are all identical to each other. And this, of course, simplifies the process of calibration and characterization of our setups. This is an image of our first generation quantum computer called Aquila that was launched in November 2022, which is still the only large-scale, publicly accessible quantum computer based on neutral atoms. It is also the largest in the sense really measured by number of qubits. It has an availability of 130 hours a week. In a week, we have 168 hours. And this is an important metric basically to allow users from all around the world to access the device essentially in real time. So the availability windows are not centered around US Eastern time, but everyone essentially all around the world can access the system in real time. We work with customers on a number of, or partners on a number of specific classes of problems that can be identified into quantum simulation, optimization, and machine learning. And based on this use, many different results, including very high impact scientific publications, have been recently published. The computer at AIST, I would love to have Ayumu perhaps comment on this. This is our second generation quantum computer. It's called the Gemini or Gemini class quantum computer, and it has been installed at the AIST. Ayumu, would you like to comment on that?
Absolutely. So thank you very much, Tommaso. And thank you all for joining this webinar. So I would like to briefly explain our computer, which we installed at AIST. So AIST is one of the largest public R&D centers in Japan. I think you already know. And basically, we installed this computer from the end of March this year. Yeah, and so we installed it. And this was originally a computer which was it was located in our Boston laboratory. And was already up and running. So, but then now, because this is an on-premise computer, we brought it to Japan, and we are now currently in the process of making it operational back to a level that it was originally in Boston. And the most important thing is because we're selling it to an external party. It needs to be, of course, the performance needs to be high, but it needs to be also very reliable, and it needs to be programmable. To a certain extent. And so that is what we're currently doing. You can see some things that are some very important things about this computer is that what is different from the one which is currently on AWS is this computer is gate-based. Yeah, so it's digital based. And by doing that, yeah, we can offer basically kind of new services to our potential customers in the future. So the reason why AIST is very interested in this machine is because they would like to integrate it with their supercomputer. Yeah, so it's basically integrating this computer, the quantum computer, with their supercomputer, which is basically more for AI. And so we are also currently working very closely together with NVIDIA because their supercomputer is based on NVIDIA GPUs. And so this is very like a three-party kind of collaboration at this moment. What AIST is looking for is that they see that the quantum computer can contribute to AI by, like, for example, like machine learning, but also the other way around is that AI can be used for quantum computing, like for to improve error correction. Yeah, so there are very many synergies which we can see between supercomputers and quantum computers, and this is what AIST are doing, and what we are also supporting them with. So we are still in the process of bringing this up, and we hope that we can launch this computer to the public sometime next year, yeah, together with AIST.
Thank you, Yumo. Thank you so much for your contribution on the recent commercial and technological success of QuEra in Japan. I also have an additional slide about that, which probably discusses a little bit more about the overall broad strategy of the Japanese government in terms of developing these technologies in the country. So let me again make a kind of step back, because we presented a little bit about the technology more broadly, how we work with the partners and customers. So as I initially identified, there are three classes: the industry, HPC centers, and governments, each one with their own goal they want to achieve. So in particular, the industry wants to use a quantum computer to redefine their own sector. And the goal, of course, is for specific big organizations in particular that are now starting to adopt quantum, to be in the lead in this journey, in this quantum journey. HPC centers all around the world, and definitely also in Taiwan, they want to use quantum nodes to be connected, as I was explaining, to their, or integrated to their existing classical supercomputers, in order to handle workloads that cannot be efficiently handled by classical computers. And this is a broad statement, and we can also be more specific in terms of problems that can be identified and solved through this technology. The other sector is, of course, governments. We will hear from Professor Kao about the quantum strategy in Taiwan, but in general, the goal is to enable economic development, upskill the workforce, the local or the national workforce, and attract potentially talent to start working on this technology, and eventually create a pipeline of people, of researchers that will then, as we will hear from Min later, will potentially join the industry and contribute to the success of these of private organizations as well. So more concretely, the way we work with customers and enable their success in this quantum path is by offering services either through the cloud or on-prem, as we have done in Japan. We also develop collaborative research, typically with high-profile research groups at universities or in the private sector, to develop or co-develop, more precisely, applications that can span across a number of different verticals. And this kind of co-design or co-development of applications can basically enable the full optimization, not only of the application, but also the optimization of the resources that from the application level are needed in order to unlock the full power of the limited technological resources coming today from the hardware availability that we have across all the modalities to operate quantum computers. I wanted to just highlight, and Ayumu, feel free to chime in if you believe this could be relevant, that the program that we've been developing together with AIST is definitely very ambitious, not only at the technological level, as Ayumu was explaining, but also at the ecosystem level. This is part of a much broader program from the Japanese government to drive economic prosperity through advanced technologies, and AIST is definitely part of this big plan. QuEra, as part of this initiative, was selected as one of the QPU provider with a major investment of the order of more than $40 million US. And here, what you see, I'm not sure, Ayumu, you were in this picture, probably.
When you I took this picture.
You took this, excellent. You took this picture. We have the Japanese Prime Minister together with our President Takuya Kitagawa, that is here on the right in the picture. And what you see here is just is a simplified version, a mock of our QPU that has been installed in the research center. As Ayumu was pointing, this project has also been done in collaboration with NVIDIA, with whom we have a strategic technical, commercial, as well as investment as of yesterday, as it was announced yesterday, type of relationship. As part of this endeavor, QuEra has been identified as a founding collaborator of the new NVIDIA the NVIDIA Advanced Quantum Center that is located in Boston at short distance from QuEra. And there are many different directions that we're exploring with them, including in very simple terms, the possibility of using our reciprocal expertise, AI and quantum, to boost research and applications in the direction of AI for quantum and quantum for AI. I will probably stop here. I would like to give the word to Professor Kao to provide an overview of the opportunities of the new Taiwan quantum strategy and see how we could potentially fit within these new opportunities offered in the region.
Okay. Yeah, thank you. So let me get...
So while Professor Kao brings up his presentation, I want to remember also for the participants that we have our Q&A window that can be accessed through Zoom, and so feel free to ask questions, of course, whether technical or more at the partnership level, to understand better how we can collaborate with all of you.
Okay. So can you see my screen?
Yes.
Okay. Okay. Thank you for this opportunity to introduce to QuEra teams about the Quantum Taiwan Initiative. So this is a national program started almost 4 years ago. So we actually are going toward the end of the phase 1 of the program. So this is a new type of program that combines government, industry, and academia. And so basically, we want to the first phase is try to identify, build a full stack system and try to identify which part of a technology Taiwan can contribute in the future if there's a quantum supply chain. So this is a collaboration between the NSTC, which is the funding agency of Taiwan. Academia Sinica is like a top it's under president, so basically research center, research institute, and also the Ministry of Economic Affairs and Ministry of Digital Affairs. So basically, they provide different incentives to work with not only the academia, also like try to promote this to industry. So In particular, there's several. So, for example, the E3, which is the counterpart of AIST in Taiwan, and they are in charge of some of the quantum research, and also we have this National Applied Research Institute, which is also hosting part of the research. Okay, so based on this initiative, the NSTC targeted the 20 research teams, and including research teams from academia, syndicate, universities, and also from national labs. So basically, it's put into 3 categories. First is the hardware technology for quantum computing. So basically, explore superconducting, silicon-based qubits, and also neutral atoms. So we do have a neutral atom team in-house, and because Foxconn is already doing the trap ion technology, so there's no support from some of the national team. And in addition, we also have some projects on photonic quantum technologies, and this is the focus on the quantum communication, also basically quantum network, and also photonic based quantum computing. So there are 6 teams which are doing software technology applications. So basically, we have different ranges of software stacks we're developing. So in terms of international collaboration, at a very early stage, we realized that Taiwan is a small country, so we need we cannot develop all the advanced quantum technology all by ourselves, and so we don't really have that much manpower. So we realized that the international collaboration is a very important aspect, not only regional or international, like through different kind of partnership. So the first success story is that we also partner with commercial companies. We partner with Finland's IQM, and because we need a test bed to test our subsystems that we are developing. So we have a custom designed 5Q superconducting quantum computer, and it's recently installed at TSI, this Taiwan Semiconductor Research Institute. And also we have another set of test bed. Basically, we want to develop the platform for quantum computer subsystems. So for now, those are all superconducting qubit-based systems, but I think the concept is in general. So we identified through this exercise for the past 4 years, we identified, okay, basically the forte of Taiwan's research is probably developing a subsystem, because we are good at nanofabrication, we're good at do the system integration, and so that's kind of the technology we identify as the future research. So because of the past 4 years achievements, and this and also Taiwanese government has put focus on quantum research. So in the president's inauguration speech, he mentioned quantum and AI, and also recently the Taiwanese government identify several AI-related technologies, and quantum is under that big umbrella. So we will secure funding to purchase a quantum computer to integrate it with the HPC, and also we identify the next few years we're going to focus on this hybrid computing. So I think that's align closely with what the QuEra is doing. So I quickly flash through some of the research highlights. So as I said, we have several teams developing these technologies, and yeah, so our teams have built a 5Q QPU, and also we have developed this quantum circuits, and we're pushing to develop a very good at least for good materials for quantum superconducting quantum devices. So there are teams trying to use a semiconductor to build qubits. Although this is very hard, but since these are CMOS compatible, and basically semiconductor technologies is manufacturing is very advanced in Taiwan. So we hope that by keeping this, maybe someday we also have another platform that the Taiwanese industry can also can move in quickly. So another key thing is the cryo CMOS. So basically, we were doing some low temperature control systems. We already have a prototype using the 28 nanometer technology. No, so it's developed by E3. So this is they are trying to commercialize this. So in terms of photonic quantum technology, we established a intercity quantum network through the commercial fiber and optical fibers. So this is the Zhonghua Telecom. So we established for about 20 kilometers a QKD link with commercial fibers, and we also have developed teams to try to build the components. And also silicon photonics. There's trying to build single photon detectors and quantum flux or chips and all that. The software stack. So we have basically cover all the stacks. So we have teams coming from a very abstract level, trying to develop sort of like a theoretical development of quantum computer science. So these are information people, and there's application layers who trying to use this for drug discovery and finances. And there are the people develop quantum algorithms, and there are teams coming from the silicon EDA, and they want to bring this technology to quantum. So they have a quantum program verification and compilation kind of team. And also we have a team which is using the real noise we get from IBM Q to model open systems. And we have a team, we have a PI who's developing several like quantum error correction decoders, which is I think achieved very good results. Yeah. So since I mentioned we're going toward the end of the phase one, and the next 5 years we'll focus on some key areas. So we will continue to develop the quantum chips, QPU and control readout chips. These are working at a low temperature and silicon photonic chips. And an important thing is that we want to be quantum ready. So there'll be quantum network deployment, and maybe we'll build a QKD chips. Finally, we want to have a on-premise quantum computer, so that we can explore for the researchers or even industry to explore possibility of quantum AI. And we have a team. We already have team who can do a very good low budget 30 qubit simulator, and we're also developing tensor network methods. And of course, we want to research toward into QC-HPC hybrid computation. So that's my presentation. Yeah.
Thank you so much, Professor Kao, for the excellent presentation and for highlighting the opportunities of collaboration with the national quantum ecosystem. The next presenter is my colleague Kai from the scientific software team. Will illustrate the opportunities provided by the capabilities of QuEra quantum computers. Kai, would you be able to share the screen?
Yes. Thank you, Tommaso. Let me share the screen. All right. Can everyone see? Can everybody see? All right, cool.
Yes.
So, hello everyone. So I'm Kai. I'm a senior scientific software engineer here at QuEra. So, for the next few minutes, I'm going to talk about our SDKs that we're currently developing, which is Blockade, that specifically designed for like programming our neutral atom or engage with our neutral atom quantum computer. So, as Tommaso mentioned about that in the earlier, that we already have one of the Aquila, which is publicly available on AWS nowadays, which is an analog mode quantum computer, and we have a Blockade SDK that is out there publicly available and open sourced. So today I'm going to introduce two new features along this Blockade ecosystems in our SDK. So the first one is the Blockade circuit. So as you know, we recently launched a gate-based quantum computer soon in AIST in Japan, and we provide like from the software standpoint of view. So we start to building this SDK that allows user to fully leverage not only write the program in the circuit representation, but also leverage our native transversal gate architecture with our SQUING, we call it SQUING domain-specific language. So with the umbrella of the Blockade circuit, we also provide a cogent to a broader ecosystem such as Cas2, STEM, and Cirq, and of course Qiskit. So the next feature that we're adding to this ecosystem is this Blockade shuttle, which is a shuttling language that allows the user to actually write a program at a low level to further fine-tune your quantum program. So as everybody know, and I will mention that in later, that one of the unique features about a neutral atom is that we do have the things called atom shuttling, meaning that our atoms or qubits can be reconfigurable during the execution of a quantum program. So all these two Blockade circuit and Blockade shuttle I provided based on the foundation of another project that we recently launched, and it's also open source, which is a QuEra. It's a compiler toolchain that we're building for specifically need for the user and us to define a domain-specific language such as Cricket and Shuttle. It also provides a compiler toolchains, a lot of the new features that we borrow from MLIR and Julia compiler community, so that we can provide features and extendability for our SDK in the next years or in the next years. Yeah. So under the hood, what's happening is that if you write a circuit program, our compiler will compile that to a low-level language, which is the shuttle representation or domain-specific language, if you like. And then eventually the compiler will take that and then targeting our gate-based hardware. So just give you, let's take a step back to give you like a feeling about how our hardware actually is doing. Sorry for that. Can you still see my screen?
Yes.
Okay, cool. Yeah, so just to give you a feeling about how our hardware is actually doing. So here you can actually see on the left side is a very trivial log depth GHZ circuit. And on the right side, what you're seeing right now is actually a real atoms that is executing this gate. So one of the things I want you to like pay attention to is that we have the ability to execute the gate in parallel, meaning that one execution or exposure of the Reaper beam can actually apply the 2Q gates, in this case is a CZ gate, to all the atoms within the blockade radius. So you can see that you're actually moving the whole row and as well as the grid to the nearest the vicinity so that they can acquire the 2Q gate in parallel. So this is what we call the transversal gate architecture, which we can leverage if you're already familiar with like the SIMD kind of architectures. In classical computer, this is kind of like an analogy of a quantum version, if you would like. So first, blockade circuit. So at the center, we have this QuEra dialects or the QuEra language that allows users to define not only the circuit representation or define the circuit program, but we also shipped with this transversal operator via broadcast, so that you can actually write a program and annotate a program that you want to use this transversal gate, and then the compiler will take that hint and then compile your program as much as possible to the shuttle level to move all the atoms into the same execution cycle or layer to acquire the gate all in once at the same time. So I mentioned that the circuit also provides you two EDSL that version with the more broader ecosystem out there already. So we do have the Kai-Hsin 2, and then we also have the extension, custom extension for parallel instruction that being built in the blockade ecosystem. It also provides STEM for bridging. So for people that are doing QC research, we also have the cogen to the STEM dialects so that you can actually leverage this ecosystem, and the compiler can go from one to another, either from QuEra to STEM or QuEra to Kai-Hsin 2 for specific research or application need. So we provide the targets framework from Kirin to actually cogen the Kai-Hsin 2 text format and STEM text format, so that we can actually, you can use our SDK and then generating the text format either from Kai-Hsin 2 format or STEM format, so that you can actually use other tools that you would like or already build with. So on top of that, we also shipped with circuit, which is that we can not only cogen a circuit for broader ecosystem again, but also we shipped with a heuristic noise model that we actually extracted from our Gemini class machine, so that you can actually start playing around with somewhat a realistic noise model for our next generation gate-based quantum computer. Of course, it's the SDK, so that it actually shipped with a simulator. It is a very efficient simulator that has multiple backend that you can choose from. We will see that in a minute. And then, of course, I mentioned that, once you write your program, our compiler written in Kirin can actually take your program and then transpile or, like lowering or rewrite your program into a low-level shuttle language. So here's an example for how it looks like. So on the left side, you see a linear, linear GHZ state preparation circuit. And notice that you can actually fully leverage all the Python's functionality, that including the structural control flow, such as for loop, to write and further simplify your program. So on the right side, here are the demonstrations for how to use our in-house simulator that has the backend only for the step vector simulation, but also a shot-based simulation, and this including the noise and circuit simulation as well. So if you're interested, there are a QR code on the upper right side, so you can actually see the documentation for further details. So again, QuEra comes with the noise channel available, so that you can actually choose all the noise, that also including but not demoed here is the atom loss channels, which is very unique to our atom shuttling, because when you shift or shuttle atom, you can accidentally lose it, and that causes an error channel. So again, I want to address that you can actually use the structure control flow natively supported by Kirin in your EDSL program. So as I mentioned about the Kai-Hsin 2, here is an example for how you can simplify a log-depth GHZ realization of the circuit by fully leverage the transversal gate architecture. So here you can see a transversal gate instructions or statements. So you can actually fully leverage that parallel instruction for targeting multiple qubit all in once, so that you can actually reduce your not only optimize your program, but reduce the execution cycle or layers of your quantum program as you need it. So finally, Squing provide a Sting cogent so that you can actually write your program in Squing as long as your operator is within the Cleaver group, and then the compiler can actually chime in and then compile this program into a Stim circuit, and then cogent it to the Stim text format, so you can fully leverage that to do your QEC research. So the next part I want to talk about is the Bokeh shuttle. Again, like on the upper right, you can see the QR code of this documentation. Everything is open source, so we encourage you to go in and start looking around with it. So once we take that Squing program, the compiler will actually be able to lower or rewrite the Squing program into a lower level EDSL, which is the shuttle level. But as a user, you can also chime in or opt in to directly writing it in this level, so that you can fully leverage and fully optimize your quantum program at the level of atom shuttling. So you can write a program to specify where and how my atom is going to be shuttled within the FOB or within the QPU, and when and how I'm going to operate the gates pulses on those atoms. So really, shuttle provides you an even lower level access to further optimize your program as you need it. And so on the right side is an example for like programming the atom shuttling with the zone that you can predefine. So on the lower side, you see the entangling zone, and then the red part that is shining on the lower part of LB is actually the Rydberg bin or Rydberg add region. So that with this EDSL, you can actually write a program to further optimize this quantum program that you really want to run on our hardware. And of course, the compiler take in and then compile this to target our hardware, and eventually we can run on both the simulator and, of course, in the next generation gate-based hardware. And so with that, here are 3 of the QR codes of our open source products or open source projects out there. Everything is open source, so we encourage you to take a look at it and start playing around with it. We like feedback. And with that, I'd like to return that to Tommaso.
Thank you, Kai. Thank you so much for the nice presentation about our software capabilities. I would like to invite Chen to upload the slides.
Thank you, Tommaso.
And Chen will talk about our quantum correction capabilities at QuEra.
So can you see my screen?
Yes, you can put it also full screen if you prefer. Excellent.
Okay. Thank you, Tommaso, for the introduction. I'm Chen. I'm a quantum scientist working at QuEra, focusing on quantum error correction. I'm excited to show more about our recent progress on quantum error correction. So the core challenge for large-scale quantum computing is fighting with the errors. Nowadays, we have the physical device with a physical error rate around 10 to the minus 2 to 10 to the minus 3. However, for large-scale quantum algorithms such as factoring and quantum dynamic simulation, it might require 10 to the minus 12 physical or logical error rate. Fortunately, we have the theoretical tool, quantum error correction, to bridge this gap. And for the audience who are not familiar with quantum error correction, I will briefly introduce the concept in quantum error correction. The most important concept in quantum error correction is introducing the redundancy, so that we can use those redundancy to detect the errors within the system during the computation, so that we can correct the logical errors. We will use n physical qubit to encode less than n k logical qubit. And there is another parameter in quantum error correction called distance, which basically describes the error correction power of a quantum error correction code, where you need exactly d physical error to create one single logical error. And the most important theorem in quantum error correction is the threshold theorem, where if the physical error rate is below some error correction threshold, then we can always use the space to suppress the logical error rate by increasing the code distance. And as mentioned before by Tommaso and Kai, on neutral atom, we have very flexible architecture. We have long-lived atomic qubit, and we also have high fidelity and parallel gates, which enable new opportunity in quantum error correction. And most importantly, we have flexible connectivity by atom shuttling. For example, if we have several logical qubits, then we can just move those logical qubits overlapping together and illuminate a global laser to implement the physical pairwise CNOT. Then by the property of the quantum error correction code, we'll have a logical CNOT. That is the so-called transversal logical gate, where allows you to directly implement logical operation and control logical qubit directly with constant control complexity. And as mentioned before by Tommaso and Ayumu, we have our first generation Aquila, which is an analog neutral atom quantum computer, which has been running on AWS over 2 years. And our second generation Gemini is the first digital neutral atom quantum computer has been deployed in Japan. And today I'm going to talk about our progress on quantum error correction on both on today's device and the device in the future. And firstly, I will talk about a key subroutine demonstration, the magic state distillation. By some resource estimation results, most of the resource during the photon quantum computation will be spent on one subroutine, the magic state distillation, to prepare high fidelity magic states. And the idea for magic state distillation is that we will need some special state named the magic state to achieve universal quantum computing. And to prepare high fidelity logical magic state, you can always use the distillation protocol to distill high fidelity logical state from noisy logical magic state. However, the magic state distillation is very expensive because those requires a logical level operation. And the nature question we want to answer is that, can we demonstrate this protocol on our machine or on today's machine? And we did this experiment on our Gemini machine by co-designing the architecture for this protocol. We found a protocol that allows us to use only 5 logical qubits, and we remove all of the conditional gate by circuit optimization, and by co-designing the circuit to utilize the control parallelism, we achieved the experiment by running this experiment on Gemini. And from the experiment, we did observe the error suppression, which matched the theoretical result, and observed the fidelity improvement at the logical level from 95.1% as the input fidelity to 99.4% to the output fidelity. And more recently, we start exploring the machine learning-based decoder with our partner NVIDIA, so that they use our magic state distillation experimental data to try to achieve better decoding result using their AI technique. And in the blog post we published together, we observed some promising initial results where their AI decoder outperformed our MLE correlated decoder, and we are looking forward to scale it up. And next, I want to talk about something in the future. So in future, when we do photon quantum computing, there will be a large overhead from the real-time error correction. For example, each time we apply a logical operator, we want to detect the error during the logical operator so that we can correct it. The way we detect the error is the protocol named the single instruction, where we introduce some ancilla qubits and couple with the system to detect the error. However, those ancilla qubits might be noisy, so that its returning result might not be very reliable. In the conventional fault-tolerant theory, to handle those noisy syndromes, we have to repeat the number of measurements by D round in general. Where D is the code distance in large-scale quantum computing, D might be at the level of 30, which will introduce 1 to 2 orders of magnitude slowdown from the physical clock speed. On the left is the conventional fault-tolerant theory with the requirement of D round of syndrome extraction. On the right, what we found is that if all of the gates are transversal Clifford gates, and we use the magic states as input and dual correlated decoding, at the algorithmic level, we can achieve fault tolerance without those D rounds, with only constant round of overhead. That significantly reduce the computational resource. And we answered this question in 2 papers, one in PRL and another one recently has been accepted in Nature. The other answer for this architecture is that can we always decode this logical measurement reliably and efficiently? The previous, the original approach to this problem is use the so-called correlated decoding, which requires to decode the hyperedge, which is in general NP hard to solve. However, in our recent paper, we develop a new approach that enables us to solve this problem very efficiently by solving the subgraph of this problem, which can be solved accurately and fast in polynomial time. And combining those results, all of the transversal-based architecture will enable practical constant time overhead for quantum computing. And putting all of the things together, we did an end-to-end resource estimation for the Shor's algorithm. And using the transversal architecture, the speed up we can get from the architecture itself is around 50 times compared to the previous estimation. Which basically reduced the computation time of the factoring algorithm from almost 1 year, which is the previous estimation, to 5.6 days within 1 week, which is our new estimation. And more recently, we want to explore the near-term opportunity in early fault-tolerant quantum computer. We don't want to apply application until we have a fully fault-tolerant quantum computer. And the key component in this neutral atom star architecture is the transversal Clifford, which enable constant overhead because of our algorithmic fault-tolerant results, and also the space-time efficient analog rotation, which enabled small angle, very efficient small angle, but also very low logical error rate at 10 to the minus 6. And based on our numerical simulation, if we have 20,000 physical qubit around 10 to the minus 6, 10 to the minus 3 physical error rate, then we can achieve 10 to the minus 6 logical error rate with the simulation volume in the quantum simulation problem around 500. And if we use the conventional method with Clifford plus D, that will require 10 to the power of 7 T gates, which is quite impossible on the near-term machine. And to summarize, we explore the key subroutine on today's machine, the Gemini generation machine, and we also explore the longer-term opportunity for quantum error correction based on neutral atom architecture. And thank you for your attention.
Thank you, Chen. Thank you for presenting the most recent breakthroughs that we have performed at QuEra. I think this is a great starting point for the final presentation by Min-Hsiu. Can you please share your slide, Min? You are also muted, so we Hey, you unmute yourself.
Okay.
Excellent.
Can everyone hear me? Okay, good.
Yes, excellent.
Yeah, we'll make it full screen. So I would just like to use this opportunity to showcase some of the outcomes that my group and also our hardware group achieved in recent months. So this is some of the research highlight that we did for the first 6 months of this year. Right now we are a small research team with only about less than 10 researchers. But in the first 6 months, we have been quite successful. We have a paper accepted in Nature Physics. This is the matrix state distillation paper, constant overhead matrix state distillation paper, and we'll show you more in the next slide. We have 2 Nature Communication papers. One is on circuit complexity, like showing shallow depth quantum circuit would outperform classical shallow circuit given some nonlinearity to those classical constant depth circuit. I think this is a very interesting result. Another Nature Communication paper is on a classical simulation of some linear properties of quantum circuit. We use classical machine learning technique, and this classical machine learning techniques turn out to be quite efficient in terms of the parameters in your circuit. We also have physical review data. This is a collaboration with universities in China. And then we also quite successful in terms of conference proceedings. So we have a QIP paper, ICL paper. So this is the leading machine learning conference. And then we also have a paper accepted in crypto. So this is the best cryptography conference. Okay. And then I have been in the international theoretical quantum computation community for a very long time. So I served in the steering committee of QIP up to this year. I served in the steering committee of TQC, and I was the steering committee chair last year. I was program chair of TQC 2021, and then last year I joined the steering committee of AQIS, and I also in 7 program committees in the last 6 months. And this 6 months alone, we already collaborate. Like these publications that I just showed you was the collaboration with 31 institutions across 15 countries. So this show you that we are very open in terms of collaborations. There is literally no limitations as long as the outcome is public. So you can see that our collaboration network also include like IMEC, IBM, NVIDIA Research, from MIT, Cambridge University, Tokyo University, and US NTU, etc. Also, because Tommaso asked me to focus on error correction, so this is like the best rework that I produced in the last couple of years. So we are the first 3 papers that construct a good quantum LDPC, and this paper also proposed a linear time decoder, which is kind of like standout. So this is different from the other 2 papers. The first one is by Pentelev and Kalashev, the 2 Russian mathematicians. Our construction are slightly different, so that's why we are able to obtain a linear time decoders. But this is basically the expander code. Secondly, we look at geometry local code. So this is geometry local quantum LDPC, because we know that there's BPT bound there. So if you further request that your error correction is geometry local, then this BTP bound in 2012.
shows that there is a constraint in your rate and distance. And our work is the first, or this middle one. So our work is the first to show that we can construct a geometry local code that saturate that BPT bound. So again, this work is well received. And then finally, this year in QIP, this constant overhead matrix state distillation paper was accepted as a long plenary talk in QIP. This is the first to show that this the overhead or the matrix state distillation step is constant, and so that this is kind of a good news for our communities. So other than that, I would like to also report the hardware progress. We use trap ion systems. It's more like the broader systems to the neutral atom systems. We set up this lab less than 3 years ago. And up to now, we could crystallize ion, like 10 qubit, 10 ions. And we also finished the state detections and qubit initializations. And in the buttons would be what the hardware team is going to achieve in the next couple of months. So they are ready to move on to prepare entangled states and also control the qubit, like implement single and 2 qubit gate on our trap ion systems. I think that's it. Thank you. I hope this is clear.
Min-Hsiu, thank you so much for the presentation, and I would also take this opportunity to thank everyone that has joined the webinar remotely. It's been a great pleasure for us to be able to interact at this moment remotely, hopefully very soon also in person with the Quantum Taiwan ecosystem. The webinar ends here. Before finishing, I would like to invite everyone who has questions to reach out to us. I put my email here at the bottom of the slide, tmacri@quera.com. So with this, thank you so much for your attention, and we look forward to continuing the interaction with all of you. Thank you so much.
Thank you. Thank you.
Bye.